talk. Thank you. I don't think Francois needs an introduction, but I'll just say a couple of words. Francois is a member of the French Academy of Science. He has a Simmons Chair in mathematics at the University of Texas, Austin. He's done work in many areas, including stochastic geometry, queuing network, etc. I looked up the genealogy, math genealogy page. It's got 27 students and 40 descendants. So it's a really great pleasure to welcome Francois. So please go ahead, Francois. You have about 50 minutes, 55 minutes. Please allow some time for questions later. But look, it's 7 p.m. in Melbourne and in the eastern states of Australia. It's 9 o'clock in New Zealand, right? It's Saturday. Yeah. So we've got plenty of time. So over to you.
Yes, sorry, very quick addition. The file with slides is available on the web, so you may.
Oh yes, I keep forgetting that. Yeah, it is.
Okay, so first, let me thank you deeply for the invitation. It's a great pleasure. I visited several times, and I even spent a couple of months in Melbourne. Years ago, and so I wished I could be with you, and the conditions would allow me to greet you in person and to thank you for the invitation. Okay, so let me share my screen and start the lecture. Okay, so share screen. Okay, start broadcast, and okay. So do you see my screen?
Yes, we do.
Okay, and my slides?
Yes. We see your slides, yes.
Oops.
Okay. Now we don't.
Very good.
No, now we don't, actually.
Oh. Okay, so I have to restart Zoom, it said, right? So sorry about that. Okay, so let me see whether I can start. Fantastic. Okay, so we are in business. Okay, so yes. So what I will present you today is work with Thibaut Taillefumier, who is on the faculty at UT Austin, and he's quite interesting fellow. He's both in math, in the Department of Mathematics, and in the Department of Neuroscience. And actually, I used to know what Hawkes processes were, but I really never worked with somebody in neuroscience, and it's a recent thing that we started about 2 years ago. Okay, and the title of the talk is Replica-mean-field limits for neural networks. Okay, so as you know, the brain is a quite large network with hundreds of billions of neurons and a number of synapses, edges in this graph, which is quite amazing. And the basic observation that Thibaut shared with me when we started this collaboration is that nobody knows what is called the structure function. And so the structure function would be an understanding that from the picture on the left, which is a network, a graph with functions, you see some edges, which are directed edges with either, excitatory edges or inhibitory edges. And a certain dynamics that I will describe maps that into what we see on the right, namely the spiking activity. And the spiking activity can be set either as on the top picture in terms of spikes, which are points of a point process, or just through the intensities of these point processes. And this is the picture on the right below, the bottom one, which gives the instantaneous rate of spiking of various neurons. Okay, so typically people believe that either the spikes themselves, which are the point processes, or their rates are encoding the information in the brain. But unfortunately, nobody knows at this stage knows how to translate the, especially for the extremely large networks that we were describing in the earlier slide, the geometry, the topology, and the nature of the graph, together with the local behavior of the nodes, of the neurons, into the point process activities that you see on the right, be it in terms of spiking, namely point processes, or rates. Okay, and so what I will describe here is the junction of two flows of thoughts, which is depicted by the figure on the right, the pictures on the right, ideas that come actually from queuing theory and stochastic network, and which were pioneered by Kleinrock and the school around Roland Dobroshin, which are techniques of mean fields, and more precisely replica-mean-fields, that I will describe, to try to apply them to this neural network dynamics. So that's one flow, mathematical flow of ideas, and there is work of Alek Borovkov on the matter, and I have a quite nice interaction with Senya and Schlossman and Sasha Rybko on the matter, which is going on at this stage, right? So but these ideas were essentially made and developed for communication networks and ideas like that, queuing theory, and not so much, as we shall see, for these neural networks. Other types of mean fields were studied, but not the replica one, right? And the other line of thought is illustrated by the references on the top, the famous paper by Hawkes, and quite nice work by Pierre Brémaud and Laurent Matsoulier. And the framework that I will describe here is the so-called Galvez-Löscherbach framework, which is now well acknowledged to be a nice description, appropriate description for intensity-based neural networks, right? Okay, what is more precisely the mathematical machinery I will describe in the talk? Point processes, parent calculus, stochastic intensity is one part. Propagation of chaos, and more precisely the Poisson hypothesis that was devised in practice by Kleinrock and really made mathematical by the school in Moscow. And the third ingredient will be lots of ODEs and PDEs that are associated with this class of Hawkes processes in their mean field limit. Okay, so to be a bit more precise, mean field approximations have been devised for intensity-based neural networks, namely networks described by point processes admitting a stochastic intensity for the spiking structure. And most, or essentially all the work which was done is in terms of the so-called thermodynamic limit, where you let the number of neurons tend to infinity and you scale the interaction, the synaptic weights, like 1 over the number of neurons. And so this leads to some very active literature, and so I learned about that through Olivier Faugeras, who is a colleague of mine. And there is a recent paper by Philippe Robert, which follows the lines of thought of this group of this activity on these thermodynamic limits, right? But the difficulty with that, or the inconvenience, is that the structure and the geometry of the network is sort of lost, and the impulse nature of the input is also lost, and we'll describe that in more detail, right? Okay, so let me describe now, after this brief introduction, please feel free to interrupt me anytime, by the way, what is the mathematical model, right? Okay, and I start with a toy model, which is this one. So it's called the counting model. So it's a special case of the Galvez-Löcherbach model. Here it's the fully exchangeable coupled neuron network with k is equal number of neurons equal to 5. There is a state which is integer valued, ci at time t for neuron I. And this state counts the number of spikes received by neuron I from all other neurons since its last spiking time, right? And so there is an integrator of spikes. You will increase your potential, membrane potential of mu at every spike you receive. This is the excitatory case. And then there is a spiking intensity, a stochastic intensity function, lambda I of t, which is linear in the state. And so there is a constant b, which is positive, even if c is equal to 0, where you spike, the neuron spikes in state 0 with rate b, and it spikes with an intensity which is linearly increasing in the number of spikes that it receives. And then it spikes, it resets to 0 in this single case. And mu is the interaction strength or the synaptic weight, and is a positive constant. Okay, and the dynamics is best described by the picture which is given here, where you see the entanglement between the point processes, which are the spiking activities of the neurons. You see that when the red neuron spikes, the green and the blue increase by 1, namely the membrane potential increases of mu, and the say green point process, for which you see 2 spikes, is triggered by a point process with a stochastic intensity with respect to the information of the state on the neuron, which is linear in that state, right? The b plus mu c. Okay, and you get the dynamics, which I think in this simple case should be clear. And you see, I mean, it's a little bit like queuing. When you have departures, you feed the queues downstream. And here you would increase the number of customers by 1, so it's about the same thing. And the novelty here is that when you spike out something, you reset. So it's like an exhaustive queue mechanism, if you want. There were modern queuing theory elevator models which had features like that, but they were not so much considered in networks. Okay, so the counting dynamics is a difficult problem. So the interesting things that you have to realize is that, I mean, under reasonable assumptions, that the constants are non-degenerate, and I mean, all these dynamics are well behaved in terms of Markov. You have a Markov chain on the positive orthant of dimension k. You can write out the infinite generator. It's not difficult. And you see, I mean, the transitions that either during at the spike time increase some coordinate by 1, all but yours. And if you're in state Ci, decrease your state of Ci. so that the coordinate bounces back on one of the Horton's boundaries, right? Okay, and the catch is that even for this one, which is the simplest case, you can work out a general Kolmogorov equations for the steady state. This chain is a nice chain. It's positive recurrence, very stable, because I mean, as soon as something gets big, because the stochastic intensity brings that to the face of the Horton, so it's very stable. It's irreducible if you take down the generate situation for the coefficients. And the only catch is that, as in queuing theory, you get a PDE for the probability generating function, say G, which is this function G of Z that you see at the bottom left. And this PDE is a transport equation, which is in a sense non-solvable in closed form, and even to understand what happens is almost impossible because of boundary terms that fundamentally come from the resets. Okay, so I don't insist on this PDE because I will discuss other PDEs, but basically from what I understand from Thibault and the colleagues in the literature working on this field, there is no understanding of the solution of this class of PDEs except in very small damage. Okay, that's what I was saying. Right, and now let me move to the tools that we use to try to tackle these problems, which are Palm calculus and the rate conservation principle of Palm calculus. Right, so I mean, this is a very classical thing. It leads to a dead end if you don't use mean fields, and that's what I'm trying to convey now. Okay, you just first write the rate conservation principle. So take one neuron, say I, and say that you just look at some sort of Kirchhoff equations, right? What comes in, what gets out. And so Ci of t is what it was at time 0. And if you have to count the number of spikes that your neuron I has received up to time t. So I denote by nk the point process of neuron k. And so this input thing will be called the interaction. And then there's the reset dynamics, where if neuron I spikes, it takes the value of C just before it's a spike, say Ci of S, and you decrease of Ci, right? So this is this integral of Ci of S and I of D, right? It's the reset. And so the principle is that you say that, I mean, this thing should increase as much as it decreases if there exists a steady state. We know there exists one. And you write the stationary rate conservation principle for first moments, which features an interesting thing. On the left, you have the input, which will be easy. So everything is symmetrical. So it will be k minus 1 beta t, beta being the intensity of any point process in steady state. And that's the interaction mean just by the division of intensity and symmetry, whereas the right-hand side, which is the reset, the decrease, which should compensate the increase, involves if you introduce the first, I mean, Campbell's formula, the Palm expectation of C just before a spike, which, thanks to Papangelou's theorem, is nothing else as the intensity in steady state biased by the Radon-Nikodym derivative, which is the intensity. It's a stochastic intensity, which is B plus mu Ci, right? And you see an interesting thing showing up that which is on the on this slide, that actually when you work out the thing, you get interesting conservation law, which relates beta, the unknown rate of the of any neuron, to actually the first and the second moment. So the first moment is linked, of course, to beta. So you get, of course, that beta is the mean of the stochastic intensity. So it's the first moment and beta are linked, but there is a second moment showing up, linking, and all these things are linked. And you can work out the thing for higher moments. You get a hierarchy of equations, and basically you are dead. you don't progress so much. And this is the way to capture that by a balance equation or RCP, rate conservation principle for generating functions. So you write the same thing. Now you take Z real number, 0, 1. You write the same conservation law, tracking the interactions, which amount to multiplying by Z. That's the increase of 1 in the generating function world. And the reset part, which is an integral with respect to Ni of the function after, which is 0, Z to 0 is 1, minus what Z was just before, which was Ci of S, which I take the left continuous here, right? Okay, very good. And you work out the same thing with an interesting, more general conservation rule, which says by the same arguments that the interaction part. Okay, so the interaction part will involve something interesting now, where you will have Z to the C. There is a 1 minus Z, which you see showing up, of course, naturally. There is a Z to the C multiplied by the intensity of another neuron spiking, which is B plus mu D, where D and C are two different neurons in steady state, and we don't know their correlation structure, right? So you see why things get entangled in a difficult way, and that comes simply from using the the Radon-Nikodym derivative and Palm calculus. And on the right-hand side, for the mean reset, same type of ideas, the 1 minus ZC multiplied by the intensity of the same guy, which is a B plus mu C, right? Where, and you see it's not closed. I mean, you can't progress because C and D are two neurons taken at random in your network of dimension K, but you don't know what their correlation structure is. So it's not even a PDE or an ODE, it's nothing, right? You simply get the balance equations, a hierarchy of balance equation when looking at the case coefficient, but you are helpless, right? And then with Thibault, we started contemplating this thing and said, oh, it would be fantastic if C and D were independent, right? And we started playing with the equations. And one day, I realized that, whoa, that's exactly what we did with Senya when we were, and Sasha, when we were working at in this queuing theory with moving stations, right? So it's just a mean field. It's just a replica mean field, which will have this independence. So, and let me explain the replica mean field model. Okay, so let me go and give directly the whole picture. Okay, so you see here I take 3 neurons because it's enough, right? You will duplicate or n-duplicate your network in n layers, right? So that's a 4-replica network model in B, right? So exactly the same topology, exactly the same structure, replicated, right? And actually, what you will do is that when a neuron spikes, the neuron has a state, so it's very, very much the same dynamic, but when a neuron spikes, say the green one, rather than sending the simultaneous information to the 2 neurons in its own replica, it chooses for each neuron one of the K or one of the n replicas at random, one of the 4 replicas at random, and send the spike there. So you see the replica 4 is chosen for the blue and the replica 2 is chosen for the red. And so, okay, and this is done independently. They're chosen at random, uniform, right? Then when you think about it, if you let the number of replicas go to infinity, you get something which is exactly what you want, namely a physical system. It's infinite dimensional. but this physical system has intuitively, and we proved it lately, the properties that we want. Namely, what we could prove, and I will not give the proof of that, is that this limit exists. This infinite non-countable state space dynamics has some tightness properties uniquely defined, and in this limit, you have propagation of chaos. In that, if you take 2 neurons in a given replica, right, their states become independent, C and D. And in addition, the routing mechanism, this new routing mechanism, which is of course cheating, but I will explain that's the only thing that we are able to do at this stage, becomes Poisson. Becomes Poisson with an intensity which is again k minus 1 beta. This beta now is for this new system, that nothing to do with the unknown beta for the true system. And so that if we can understand what happens for a single neuron fed by, in that case for k is equal to 3, by a Poisson point process density beta, if you can solve that, if you stipulate that this beta should be such that the output rate is also beta, then you can understand what this Replica-mean-field limit is mathematically, right? Computationally. Is the idea clear? Mm-hmm. Okay, good. And this Poisson, this is so there are technicalities, and beautiful ones, which are to prove the Poisson hypothesis, or equivalently the propagation of chaos. At the level of ideas, things should be, I mean, you would believe in it, right? So, because I mean, you keep the mean and of the intensity of arrival, and you have like superposition of rare independent events, or they're not quite independent in the prelimit, they are not, right? But so you believe that it's Poisson, and it's possible to prove it. I will say a few words on that, on what we did with Michel Davidoff lately, right? Okay, very good. And so, but the thing is that the idea comes from stochastic network, and now there is a proof of this in a recent preprint. So the preprint in question is only in a discretization in time, but lately with Michel we could prove the propagation of chaos in the continuous model, right? Okay, so let me say a few words because I will compare them later of connection between the thermodynamic and the replica mean fields, right? So in common, they use a model with stochastic intensity based spiking, and they lead to asymptotic independence, okay? But there are key differences. The thermodynamic sort of lets the geometry vanish, the finiteness of the network vanish, in K disappears, right? And requires interaction scaling like 1/k, so that you get some sort of fluid input to neurons, whereas the replica keeps Poisson and I mean point process inputs, keeps the geometry and the structure as is, and just replaces the only unknown, I mean, difficult object in this in these structures, which are the input point processes, by Poisson. And okay, and leads, and both lead to consistency equations, which okay, but the key plus of the replica thing or idea is that you keep the geometry and the finiteness structure of K, and just play with the temper with the point processes, right? Okay, so that's the okay, and so we should not. I mean, these are just caricatures. I mean, we should understand that these things are just, you are helpless for the general problem, and what you do is you have to try to simplify it and to see, I mean, as one does in a caricature, which one tells you interesting things and more appropriate things on the true problem. Okay, so you should not put too much value on these things. These are just, I mean, simplifications on the problem that nobody can solve, but with the understanding of what the simplified model exactly is in terms of probabilistic structure, which is this infinite dimensional nonlinear Markov chain, right? In the sense of the Doboshin school, right? Okay, good. Let me go through the key observation now, which is that you do this simplification of this caricature because you can solve. And let me explain this. So you remember the RCP for the genetic function, and it was involving the z to the c d on one side, and the z to the c c on the other side. So the last one is easy. Z to the c times c is just the derivative with respect to z of the generating function. And so, the difficulty was with CD, but now CD in the mean field become independent. And so D is like C, but independent. So it's like beta, right? And hence you get actually an ODE, which is written here, which is order 1. So the Z prime linked to Z through an unknown quantity to be specified, which is beta. Where beta should solve the self-consistency equation, which is written, where is it? I don't see my self-consistency equation, but it just says that it ought to be that when you get g of z, its first derivative, which gives the mean of c, should be such that mu plus beta plus b, the mean should be no, b plus mu times the mean should be beta, right? So that's a self-consistency equation that I will, this is the linear things that you see in mean fields. And this is the analytical result. This ODE, it's not a big deal as a unique solution, which is a probability generating function. And you can solve it in closed form. And that's the solution is given below. On the bottom, and if you set A, which is k minus 1 beta plus b over mu, C, which is k minus 1 beta over mu, the self-consistency equation in the end reduces to the thing which is given here. You see beta is a nonlinear function of beta, which involves the incomplete gamma function at A and C, which are the constants I just described. Right? Okay, so who cares? But it's solvable in closed form, and then you can really understand at least the Replica-mean-field limit in this symmetrical case. Okay, so that was just a warm-up. The general case is the so-called linear Galvez-Lasher-Bach intensity-based model, which was introduced by Antonio Galvez and Eva Lasher-Bach a few years ago. So let me describe the dynamic in words. So the same type of dynamic. So I describe it through an evolution equation and this function. So there is a new thing which is called relaxation. So that you see on this picture. So you see there is for each neuron a value bj to which you relax exponentially, right? So and this translates into this equation, evolution equation, bi minus lambda I ds, right? So this, if you are below, you decrease to that exponentially. If you are above, you decrease to that. If you are below, you increase to that at an exponential speed, right? Which is okay, good. You have the interaction term. Now the mu ij are general, so they're positive. It could be 0. So you can devise a purely feed-forward network, a cycle. I mean, any topology. And the reset now is in terms of the state variable. I should have said that first. Is the stochastic intensity itself, right? So. And therefore, now the stochastic intensity increases of mu ij if the synaptic weight between j and I is mu ij. The state variable relaxes, as we said, and the reset now is with respect to the density. It was lambda I before the spike, and it reset to a value Ri. Which is non-negative okay, so this is the evolution equation. These are the types of dynamics that people have devised for neural networks, right? Intensity-based neural networks. Okay, then you work out the same jazz. I mean, nothing new. The grasping the ideas for the special case allows you to grasp them in the general case. So you write the rate conservation principle now for moment generating functions, e to the u lambda I, right? And so you work out the rate conservation principle, and again, you find an interesting set of equations which are neither ODEs nor PDEs, nothing, because they involve the joint distribution of lambda I and lambda j that you see in the equation at this place, right? So this, you see lambda I, lambda j, and you don't know that, and you are helpless. And then you work out the Replica-mean-field, which works like the same way. And in that one, the only ugly thing or known thing, lambda I, lambda j, that you know nothing about, factorizes, and you know a physical system implementing that. So you discuss something which makes sense. And it solves now a nice collection of k ODEs related by conservation, nonlinear conservation equation between the betas. And this ODE is of the same, this collection of ODEs, there is one per neuron, involves, of course, partial derivative. So it's a one-dimensional ODE. So it's a first order, L prime now of u times something, plus Li of u times something, which involves both the interactions and the relaxation, plus known function, the beta I e to the u ri. Ri is the reset value, is equal to 0. And in addition, if you differentiate Li at 0 to get the first moment, then the B's that you have in input there should give you the mean, the beta I that you get for the solution should be self-consistent globally through the set of k ODEs, right? Okay, so if I give you the beta in input, the beta j in input here, right? Plus the beta I due to this term here, right? It defines an L function, and if I differentiate this function at 0, I get the consistency things that the beta I should be the mean there, right? This is the nonlinear self-consistency equation of the Replica-mean-field. That's the thing. And the same story, it's a bit more complex, but I mean, nothing deep. You solve a specific ODE, you find closed form expressions. They involve the exponential integral function now. Well, nothing important. The important thing being the that actually you can, in this mean field replica, this replica mean field caricature, you can solve the problem, which was k-dimensional and intractable, as a collection of one-dimensional problem coupled by nonlinear equations, self-consistent equations. Okay, and okay, so of course, I mean, there are interesting things on the existence and uniqueness of the nonlinear equations that I will not describe. That we describe them in the paper, right? Okay, so let me say a few words, I mean, out of that, so you can analyze first, I mean, since you get this solution, the structure of what we call the response function, namely from the input of the other neurons. If you know the rate, what is the output rate of the neuron, call fi this function. So it's a function of the betas and the synaptic weights. And we proved that, and this is interesting because it's very different from what happens in the thermodynamic limit. We could prove a certain number of, express them in the simplified case where the base rate bi is equal to the reset value ri. That for fixed mu, when the betas become big, things, the response increase like a square root of the input, the total input rate. or increase rate of the betas. So that's sublinearity in the input. And the notion of saturation in mu, now you fix beta and let the mu's increase. And actually that goes to a constant, which is known explicitly, as you see in the equation. So, I mean, one can understand out of that, I mean, structural results like that. But mostly, the most interesting thing is that you can now try to compare with a classical thermodynamic mean field. And at least for things which pertain to what these neural networks exhibit, namely the sparse case, when neurons interact. So this is an acyclic network. You see, I mean, the structure in blocks. You represent the weights. The white means 0, and the colors indicate the way the rates, the synaptic weight are sampled. And you see there by block. So from block 0, you go to block 1, from block 1 to block 2. So it's an acyclic network. And at least in the sparse case, but also in the other cases, in the sparse case particularly, you outperform very significantly in terms of quality of approximation. So this would be a representation of the simulated rates. The ground truth is on the diagonal. The red cloud is the thermodynamic limit, and the blue cloud is our replica-mean-field, right? So I mean, so in short, to make a long story short, I mean, in the sparse case, which is an important case, this does better, which is normal, because in a sense, you keep the random structure of the input processes, right? Whereas this is fluidified in the thermodynamic limit. Okay, so let me. How much more time do I have? Hello?
Sorry. I was trying to unmute myself. You have another, let's say, 10 minutes. Is that okay?
Oh, very good.
15 minutes.
Okay,
as I said, don't, take your time. I think we.
Okay. I was perhaps a bit fast. Sorry, but let me. Okay. Let me now describe an idea which is the one we have been working on lately, which is the pairwise interaction model. Okay, so it will be the pairwise interaction replica-mean-field limit of the Galvez-Lercher, the linear Galvez-Lercher-Bach case, right? So, and let's recede a little bit from what I said. So the big picture is that you have a k-dimensional problem, which the poor humans cannot solve, right? Okay, at this stage, right? So then, I mean, the natural idea is that, oh, I can solve the one-dimensional problem, okay? So let's look at the best caricature, which is a collection of one-dimensional problems, and entangle them through this nonlinear consistency equation. That's what mean fields are all about, right? And there is a physical system which embodies that, right? So it's not just nonsense that you say, oh, let's say that 2 + 2 is 6 and see what happens, right? No, it's a physical system. It's a real system in sense. It's infinite dimensional, but it has it has some form of reality, right? Okay, but then you say, oh, why not looking now at systems where rather than cutting things in terms of one-dimensional objects, you cut them or partition them in objects of dimension 1, 2, or 3, and something, and then you entangle them by nonlinear conservation equations, self-consistent equations. Okay, and it has not been done in queuing theory so much from what I understand, but here it's very important because people think that correlation structure between neurons are an important signaling quantity, right? So, and it turns out that we realized that we could solve using this approach, analytical approach, the two neuron case, and then work out a decomposition of the replica-mean-field type for a partition where the elements of the partition are not single neurons, but pairs of neurons, or pairs and singletons, right? And so let me explain the first. At this stage, no mean field, nothing fancy, just an open loop system with 3 types of Poisson input: the purple that feeds the left network, the left neuron, the orange that feeds the green neuron, and the central one, input process with rate Poisson, with rate beta I, and assume they are independent, that feeds simultaneously neuron 1 and neuron 2, right? With this sort of fork activity that, I mean, when beta 5 has an event, that creates simultaneously an arrival in 1 and 2. Okay, in neuron 1 and neuron 2. Now, neuron 1 and neuron 2, they interact by the book, right? So when lambda 1 spikes, that sends a spike to neuron 2, which exactly at the same time, when there is a reset on coordinate 1, coordinate 2 increases of mu1 2. And conversely for the 2-to-1 interaction. So it's just the true Galvez-Flerscher-Bach network of dimension 2. Now each neuron has its own linear stochastic intensity, and you get beta 1, beta 2, which are spiking point processes, which are not Poisson, with certain intensities, beta 1 and beta 2. Okay, and it turns out that in the same way as so in queuing theory, all the work by Fayol and Jasnogorsky and Malishev, all these type of things, and you could solve the 2Q problem. You can also solve this one. And it's interesting, as we discovered, so we spent a lot of time on that. It's a bit more technical now, but you can solve these 2-dimensional. So now you have a moment genetic function of in 2 variables, L of u, v, and you get an interesting transport equation with non-locality. So it's written here. So I give the general equations, the general equation for this, and so you see the difficulty comes from the fact that you get now partial derivatives in the 2 variables at specific places, u is equal to 0, v is equal to 0, that account again for the resets, right? So that's the catch. Okay, and so but this one we could solve. We could solve. I will not explain how. It's interesting, but so by analogy, it's like what all these authors I mentioned used to do. You reduce that to integral equations which are solvable in closed form, and so we even have for the certain number of explicit closed form solution. For instance, when some of the input point processes do not exist, beta 5, which creates difficulties, right? Okay, so to make a long story short, the important idea is not there. The important idea is that if you know the solution of this PDE, and we do, you can get, of course, the mean, not only the mean as we used to do, but the correlation structure of a given pair by differentiating the unknown function L solution of the PDE at 0, 0, right, in UV, and of course the second moments, but the correlation is the interesting thing. Okay, and this is extremely rich in terms of behavior. So we looked at various dynamics, topological structure for this 2-neuron Galvez-Flerscher-Bach thing, and looked at again the response function in beta 1, beta 2 as a function of the input and the structure of the weights. Okay, so it's closed form for some cases and explicit in terms of integral equations in the general case. Okay, but the main point is here. in terms of novelty at the level of ideas, answering a question that people had in mind as being, I understand, important in neuroscience, which is what we call the pair partition replica-mean-field model. So it goes like this. You partition each replica, now not in a collection of singletons, but in a collection of either singletons or pairs, okay? And with a special emphasis on pairs on which you want to see the correlation function, okay? And each replica is partitioned the same way. There is a set of singletons in the typical, in the unique partition. It's the same in each replica, and there is a set of pairs. And actually, what we proved is that under the in the limit, the joint moment generating function admits a product form, which is a product on the singletons of the partition of the solution of the ODE of the first part times a product on the pairs of the solution of the transport non-local transport PDE in two variables for the pairs, right? Lij of ui uj, right? That's the okay. That's the main thing, and then you work out the self-consistent equations. Okay, so you take your ODEs, you differentiate the solution Lk at 0 and get beta k. You differentiate the two-dimensional one Lij at 0, 0 with respect to u and to v, and you get the beta I, beta j. And that gives you, I mean, the self-consistent equation, which constitute the extension of the ones we considered earlier for the pure ODE one-dimensional partition case, right? Okay, and this works very well. It beats in terms of, I mean, caricature. Of course, singleton replica-mean-field. And for the first time, it allows one to give, so here is an interesting case, which is important in neuroscience, where you get, say, a binary tree with first neuron 1. So call it Adam, it has 2 children. The interaction between these 2 children is important, right? So these are the, this is this singled out pair. And then each neuron in this first generation creates a second generation and blah, and blah. And you get this binary tree. And there is, of course, a natural structure, which is the decomposition of these neurons. In this partition, then you replicate this tree an infinite number of times. You randomize the outer edges, the blue edges, in the replica-mean-field way, and you get the pair replica-mean-field for these acyclic neural networks, right? And okay, so it works much better than the one-dimensional case of the singleton case. And as I said, for the first time in large networks, it allows you to analyze the connection between the signaling, with probably the signaling are the rates, the betas, and the correlation structure, right? So that's what people are interested in this application, right? Okay. So I think I'm done. I want to leave the time for discussion. So as I said, this is what joint work with Thibaut. Thibaut and lately Michel Davidov. So we have 2 papers on that, and we are actively working on this. So the people interested in that are people in applied dynamical systems. So it's a SIME journal. So the work on proving the mean field, namely the proving the Poisson hypothesis, and so we cut that in 2 parts. We have a first part on the discrete time analog of that, which is part of the thesis of Michel Davidoff, and we are currently we now have a full proof of the continuous time, but it's not in print yet. Okay, that's it. Thank you.
Thank you, Francois. That was a very, very interesting talk. You certainly had my neurons firing at a very high rate. So, okay, questions and comments.
So, Francois, am I audible?
Yes, you are, Andrew.
Good, that's good. I was a bit lost as to where the structure of the network comes into the picture. You mentioned at some point the sparse case being important, and I guess in the sparse case, randomly chosen neurons are more independent of each other than otherwise. But is that the sort of intuition behind this, or have I lost it completely?
Yeah, no, I think I went a bit fast. Sorry about that. But so in the first model, the toy model with the counting case, there was basically no geometry, no structure. It's only in the second model where I said that the mui's could be 0 or positive, right? And there, it's out of that you can represent networks like the one I represented in the last picture, say purely an acyclic structure, a tree of neurons where the first set of neurons spikes on the second level and the second level on the third and so forth, right? So the geometry is purely captured by the structure of the graph, which is purely captured by the mu ij. And generally, the collection, let's look at the one-dimensional problem, the collection of ODEs capture in a hidden way the geometry of the graph. There are k ODEs, and they are linked by exactly k parameters, which are the beta i's, which lead to this nonlinear self-consistent equation. So the geometry, the finite geometry, is captured in the k ODEs and which have in themselves the mu ij, which is the geometry of the graph, and they lead to this and everything is captured by the nonlinear equation, self-consistent equation between the betas. Okay, then what you ask the second question more is very natural, right? And you're right. So indeed, so what is the difference between, so the two tools which are available, perhaps one people will come with others, but the two known tools are either the thermodynamic mean field, where you get the single object, the single neuron would have a fluid input and then spike. And so, okay. And so when you have a large number of large number, the degrees are large and interactions are strong, but the degree is large is exactly non-sparse, right? Then you have indeed a strong law of large numbers, and things are sort of in some scale constant plus fluctuations, and the thermodynamic limit is more reasonable or less unreasonable in this case than it is in the sparse case, right? So the question is, when is the impulse nature of the input point process important? And it is in the sparse case, right? In the sparse case. So then the other question is, well, is Poisson the right model? Okay, so, but Poisson is the only one for which you get a physical system that embodies the equation that you can solve. And so Poisson is the poor man's, I mean, the poor mankind solution that we have to resort to because nobody knows how to do better, right? Because Poisson it comes from the replica and the Poisson hypothesis. It doesn't come from the fact that we measure that there are Poisson processes there, right? It's just it's why we to be honest, we call them caricatures, right?
Thanks.
Okay, but so Poisson, this being said, I mean, the second line of thought at the end, where I was showing how to interconnect by the same machinery pairs and not singletons any longer, then it's not true, right? The inner structure is preserved, and so the inner flows are not Poisson, right? And the output, of course, is never.
Guys, may I comment?
Please do, Kostya.
Yep. Just a quick comment. I sent our 2014 paper with Decoise and Gilson to Francois today only. It's also about modeling networks of neurons, but without any limits. It's about solving, finding stationary distributions, and it's more realistic in the sense we include what's called Hebbian learning. That means synapses become stronger when there is a certain order in which neurons are firing, and also the existence of so-called absolutely refractory periods, which means that if you're a neuron and you just fired, then for a certain time you can't do anything. So you need to refresh to have some rest. So and we were able to find stationary distributions in some sense, approximation to them. Would be very interesting to compare how it works. And there are also analogies with queuing theory, of course. Our approach was originally closer to Brimont-Mousselet, but then we deviated. And another thing is, I will just in chat. It turned out that today there is an event in France. There is one-day workshop to celebrate 90th anniversary of Raphael Khasminsky. And it's organized, it's happening in Le Mans University. So if you have got time to attend after this talk, you can proceed along this link and see what happens there. Thank you very much.
Thank you, Kostya. That's that's an interesting.
I will study. I will study your paper, Kostya. I didn't know about it, and that looks quite easy. And so the 15 minutes elapsed between the time I received it and the beginning of my talk didn't give me the enough time to look at it at this stage. But the refractory thing is quite interesting, and I learned from Thibaut that it's a very important thing. So there are lots of very interesting variants. There are those also where firing is linked to heating times, right? You have a stochastic process, and the first time you hit a boundary, then you spike. And the boundary is a random process. So Thibaut is working on that. I don't know about these models at all. But there is an extremely rich variety of neural structures. And the key difficulty is to try to have something that mimics really what they call the structure function, right? So I give you the geometry and the cinematic weights. Please give me what happens. And so that's there is no in queuing theory. You have product form. You have lots of very beautiful things. Here, there is nothing like that, apparently.
So is there some consensus of like what the geometry of real neural networks is in your brain? I mean, does it look like this binary tree? I mean, I hope not.
Probably not.
Yeah. So it's very important question. So and indeed, so first it depends on functions, right? So I mean, for instance, the cells which are in charge of analyzing pictures. The part of the brain, there are these grid cells, perhaps you heard about them, which are about the geolocalization of, and these are fantastic things, right? And so you can't give a generic answer. So there are some functions, these are circuits, I mean, part of the things, and I tell you what I heard, I mean, I have no knowledge at all on that, right? So, but depending on the function, there is a topology, right? and so of course what you have in addition is that this is sparse, right? So you don't have very big degrees. You don't have, like in the internet or the so-called so these power laws or things like that, right? So I mean, it's a structured network where in some areas you see certain topology, and infinity different function, and the degrees are not like some neurons having. It's just physically impossible to have. I mean, like some degrees tending to infinity or things like that, right? So it's sparse, and the answer to your question is that it depends. The topology depends on the function, and the topology is meant for the function. There is another neuroscientist at UT, Ila Fiete, who explained me how these grid cells work. They are our representation of Euclidean space. When we move during the night, you move in your bedroom, right? You know where you are. How is it? Because of the grid cells. And so, and it has a very interesting structure in layers, which is fundamentally acyclic, and it uses the Chinese remainder theorem to help you locating where you are. These are amazing things, right? So, and so our representation of Euclidean space, and the same thing for all animals, all mammals, including bats, but bats have it in 3D. Rely on the Chinese remainder theorem and is based on the specific structure of neurons, which is fundamentally layers with acyclic connections. It's, I mean, mind-blowing things, right? When you talk to these people, and nobody knows how to map the topology into the function, into the function in a very weak sense, even the rate of the spiking activities, right? So that's quite amazing field.
I put a couple of comments in the chat box. You know, very famous first success, completely mapped, not human, but animal's brain, 302 neurons, a small nematode worm. But a more recent one, it's actually 7th of June this year, article in New Scientist. It's about mapping of a part of human brain, 50,000 neurons. So what's the size? It's petabytes, 1.4 petabytes. That's what this map takes.
Sorry, what's a petabyte?
Petabyte, it's a lot.
Excuse our ignorance, but
Guys, it's huge.
I know, yeah, I get it that, but